All right, welcome everyone, all my fellow HVAC nerds. Today is Thursday, it's 10 o'clock. We know what time it is. It's coffee break time. We got some cool prizes today. One I want to specifically mention, we're going to do a little auction at the end. And if anybody wants to play hooky and go to Rocky's opening day, we have 4 tickets. So we're going to do that at the end. Little auction. We're also going to have our normal prizes that we'll go through at the end. But you didn't come here for that. You came here to get filled with some knowledge on the channel blender products right here in Denver, Colorado. We're lucky enough to have Travis Starnes. He's going to take it away from here. Go ahead, Travis.
All right, thanks, Andrew. Let me bring this up. So yeah, thanks to Long for allowing us to share some information about our channel blender technology. I am Travis Starnes. I head up our HVAC segment within Blender Products. We've been providing mixing solutions for a little over 50 years now, applying technology to solve various temperature, velocity, and other stratification issues in a host of industries, including the HVAC space. As Andrew mentioned, we are a local company with a unique focus to apply best engineering practices to what we think is predict and accurately measure performance and mixing effectiveness for our products. Throughout our history, we've delivered around 225,000 different mixing solutions installed in a variety of applications. So for today's talk, we've been providing a lot of solutions around stratification inside AHUs. That's our centerpiece of our technology portfolio here at Blender Products. We tackle a myriad of stratification issues, but for today's discussion, I wanted to focus on temperature stratification. So we'll level set around temperature stratification in cold weather environments like we have in our own backyard. So what you see here on this slide is temperature stratification really exists in an AHU when 2 different air streams, like an outdoor and return air, enter a mixing box or an economizer section. ASHRAE references this in their materials, and I've listed a couple here on the right-hand side of this slide. But this CFD illustration is a particle trace showing inside an AHU as the outdoor air and return air, they kind of bounce off of each other and stratify inside the plenum. So contrary to common practice, there really is no orientation of the outdoor air and return air dampers in this mixing box walls that can effectively address this issue, tackle the root cause of why we see temperature stratification. Therefore, you will experience freeze stat trips, or even worse, leading us to the conclusion that mixing boxes don't mix for this particular configuration here. So ASHRAE references this. For those of you who follow the ASHRAE journal, there's been 2 articles in the last 14 months of why mixing boxes don't mix and how effective are mixing boxes at the economizer function. Obviously, with our technologies, we think we have good solutions for these. So I would encourage you to go find these articles and then reach out to Long or ourselves to discuss various solutions to tackle these problems. So ultimately, it comes down to cost is a big driver on projects. But ultimately, what we think is extending economizer operations. Too many times we see where when the outdoor air ambient temperature reaches below freezing levels of 32 degrees or below, we see either control schemes that are integrated to minimize the impact of that, or they just, shut off ventilation entirely. But obviously in today's environment with ventilation requirements, that adversely affects indoor air quality, but ultimately utility costs are rising. So what you see on this plot on the right-hand side is the y-axis shows annual operating costs for the year, and then you see blended electricity rates. That blended electricity rate is the demand charge plus the consumption of kWh. So demand charges, for those of you who don't know, that can be significant. That can be 60, 70, even 80% of a big building, a commercial building's utility bill. So typically in Denver, we'll see rates anywhere, a blended rate from 0.06 to maybe 10 cents per kilowatt hour, but you can see in Denver and Minneapolis, in those cold weather environments, there's significant money to be had in terms of cost savings if you can simply extend economizing between the temperature ranges of 30 degrees and 10 degrees Fahrenheit, so that you don't pre-abandon economizer operations in your AHU. So the channel blender, as Andrew mentioned, this is one of our latest technologies that we think is kind of a superior technology compared to the other Series 4 air blender that we've had in the marketplace. But really, this was born from a technology development exercise back in 2015. We reached out to the marketplace. For those of you who are familiar with our static mixing device called the Air Blender, we were reaching out to clients to see why we weren't getting more uptake into AHU designs. And what we found was that people certainly liked the mixing effectiveness of the Air Blender, but the penalty of that was downstream mixing distance. And so they challenged us if we could come up with a mixing device that did not compromise mixing performance, but we could do it without the footprint, then we might have an area of the market that might be underserved. So the channel blender is a new means of combating stratification inside air handling units. This product is used in the mixing box in place of traditional outdoor and return air dampers. This mixing approach addresses the root cause as to why dampers in mixing boxes fail to reduce temperature stratification, while eliminating one of the greatest penalties with using our static mixers, and that's the additional tunnel length or the extra mixing distance required. So it eliminates that blender section downstream of those static mixing devices. So how does it work? So what you'll see on the left-hand side is a rendering, a 3D rendering, where we remove those outdoor and return air dampers and we integrate them on the discharge side of the channel blender frame. So those are removed from your traditional mixing box. That mixing box is then sucked up tight against the ceiling or the back wall of your return air, and it creates a tight seal. As those air streams enter this channel blender frame, they're met with they're double-walled insulated channel walls, and it partitions this air into tiny slices. When I say tiny, around 4-inch slices. And then those air streams stay separate from each other. And the only time they come into contact is when they exit those blades, the damper blades on the discharge side of the channel blender frame. And that's where we promote heat transfer from one airstream to another. And so you can see the homogeneous stream right upstream of that filter section. So that's how it works. The close proximity of these different airstreams will promote heat transfer, and we use the damper blades to create small collisions outside of that damper frame. So the channel blender is designed to remove freestats, but also extend economizer performance. The channel blenders are custom designed. Now, I don't want to scare you with custom design. What we've done here at Blender is we use various modeling tools to take our selection sheets and produce a shop drawing package in a fairly short order of time, so that we can customize each channel blender and fit inside of a unit. So the dampers we don't lose any functionality in terms of control scheme. The dampers and actuators, as you can see in the photo, are on the downstream side for service. So typically in most applications, what you'll see is we will share an access door with either the coil section or the filter section. And we use that to access the actuators as you would in a normal traditional mixing box. We are seeing more and more requests for, given the importance of ventilation and measuring that outdoor air into occupied spaces. So if you do have a requirement for a dedicated minimum outdoor air duct, we can do that into the unit, which I have a rendering I'll show you later. But long story short, I wanted to mention that we've done 18 different configurations where we have air inlets going into the channel blender. So if you have an atypical application or something that may require special engineering know-how, please reach out to Long and they can help assist you in getting a channel blender design. So here's kind of our base case. This goes back to the CFD simulation shown earlier. On the left-hand side is a mixing box, standard 44,000 with a 25% minimum outdoor air requirement, and air is coming in at 16 degrees Fahrenheit. So what you'll see, the control system is asking for a mixed air temperature of 55 degrees. And while we satisfy that requirement, there is a cold spot towards the ceiling of 19-degree air that's going to propagate through the AHU tunnel. And that's going to cause issues with the downstream coil section, nuisance freestat trips, and all those sorts of things. At those controlling, modulating positions for the dampers, we estimate a delta P of around 0.15 inches. So all that's with no mixing technology integrated into the unit. You take that same mixing box and you integrate a channel blender into that space. There's no additional footprint needed for the AHU, but we've raised that minimum temperature from 19 degrees Fahrenheit up to 46 degrees Fahrenheit. So you can see just by the temperature contour plots, that gradient is much tighter now. There is no free lunch. There is an additional delta P. We do require some energy to mix that airstream. So when you look at the total pressure drop across the channel blender frame and through those dampers in a control position, the total delta P is 0.41 inches, or approximately a 1/4 inch net increase to the overall system. So the other thing I wanted to mention is not only temperature stratification, but we are seeing more and more requests for applications which require enhanced uniformity. This same 44,000 CFM 25% min, we did a project where we're seeing our channel blenders being installed as far south as Florida in hospitals, and obviously not for temperature issues, but humidity control in occupied spaces, specifically surgical rooms and those sorts of things. So we take that same base case where we have outside air coming in at 90 degrees with 75% relative humidity, and we install a channel blender. We've reduced the variability of moisture loading to that coil so it can knock out water in a more uniform manner, and they have better control of moisture levels inside those occupied spaces. And I got a case study that'll speak to that later on here. As I mentioned, each one of our channel blenders is a custom package. We do perform CFD on these units, and the reason for that is we want to ensure performance of these. And so we'll perform CFD at maybe 4 to 5 different operating conditions to characterize the delta P and the mixing effectiveness at at various points on the economizing curve. We'll submit a report to you. We do get the question of, well, how much space do you really need? So typically I tell people, I would say anywhere 8 to 12 inches downstream of that damper plate on the discharge side of that channel blender frame. If we could have 12 inches downstream of that, we think most of the heat transfer will happen up in that short section, to where by the time it reaches the flow straightening vise, like the filter section, we're good to go. Pressure drop ranges anywhere from 0.3 inches on the low side up to about 0.6 inches on the high side. I will tell you that we are working on, we think that might be a little bit on the higher side in some applications, so we are working on new designs to lower that delta P by about 25%. Again, I would encourage you to reach out to Long to discuss channel blender performance. So here's a case study where the impetus for this project was really poor humidity control going into 2 surgical rooms. In addition, during the winter season in Albany, New York, they were obviously seeing temperature drop below freezing, and they would get freeze stat issues to compound the AHU performance issues. So what we did, this is a retrofit unit. We could not grow this AHU in tunnel length, so the static mixer was was not considered a solution here. So we installed the channel blender. We removed the weather hood and dampers from the side entry. This is a side entry unit, and you can see that we did have a dedicated min on here. So we had an airflow measurement station installed right on the outside of this this section here of the AHU in that photo. But what you see, since we installed this channel blender, we went through 2 winter seasons, and we've had 0 recorded freeze stats during those winter seasons. And also we've added an additional 2,100 hours of extended economizing hours. So that saves them additional operating costs. And we're also continuing to gather data of what the RH control is into those surgical rooms. So the client is happy with this, and they've actually just extended more channel blender orders to retrofit other units at this hospital. So ultimately, a lot of drivers for these projects we get as payback and financial. So here's a case study in Denver, Colorado, in our own backyard, where we take that same 44,000 CFM unit at 25% min. And if we can simply operate this unit between the temperatures of 10 degrees and 30 degrees Fahrenheit, what does the channel blender do in terms of payback? We've added significant hours there. You can see the bin data there on the left-hand side. But just in Denver, just a payback for that channel blender, if you just did equipment costs only, the savings there when you look at the compression, the extra energy, the electricity going into those compressors, if we save that and we can get free cooling when we're using the air side economizing, payback is typically less than 2 years at various electricity tariffs. So with that, I know this is a coffee break series, and that's a lot of information, but I would encourage you to reach out to Andrew Tobin and colleagues at Long. And so Andrew, I would like to pass the baton back to you.
Thank you very much, everybody. Again, I am Andrew Tobin. Travis Starnes was our presenter. This was a great day. Next week, we have Josh Likes from our Grand Junction office. He's partnered up with Griswold Controls, and they're going to talk about the evolution of control valves. So everybody, thank you very much.